Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're delighted to have Daniel Kane here with us to tell us about the FT-Mollification Method.
Hello, I'm here to talk about the FT-Mollification Method, which is a method that Jelani and I, and maybe a couple others, have been recently developing to work with a number of problems dealing with polynomial approximation and dealing with k-independent random variables and such. If you saw Jelani's talk yesterday, probably he discussed some of the techniques in application to that one problem. Well, let's get started. So first, a brief outline of what I'll be talking about today. I'll start with an introduction where I'll describe some of the basic concepts that we'll be dealing with and what sorts of problems we're dealing with. I'll then talk about how we can use this method to show that k-independence fools linear threshold functions. I'll then talk about some ways of generalizing this technique and how to deal with fooling several linear threshold functions at the same time. I'll then move on to fooling degree 2 polynomial threshold functions and move on to the conclusion. So to start off with sort of one of the basic problems that we deal with using this method are things involving k-independence. So we define a collection of random variables x1 through xn to be k-independent if any collection of k of those random variables are independent of each other. And why should we care? Well, importantly, for computer science, k-independent families are easy to produce. You can create small seeds that produce k-independent families, which is good for doing de-randomization or producing hash functions or something. And furthermore, even though you can produce them with much lower entropy than fully independent families of random variables, k-independent families often behave like fully independent families. So hopefully, if something were going to hold for a fully random family, it will also hold for a k-independent family if k is large enough. So in what types of ways might we want our k-independent random variable to behave like fully random variables? Well, one of the standard things we might want to do is fooling various functions. So this means we have some function and we'd like the expectation of that function to be correct. And we'll get into what types of functions later, but in general, in this talk at least, we'll be talking about sort of polynomial threshold functions. You apply some polynomial to the variables and then see whether it's positive or negative. And if you have some algorithm where whether it works or not depends on whether some polynomial in the variables that perhaps you don't know ahead of time is positive or negative, then being able to fool your polynomial threshold function means that your probability of success is maintained. So to talk a little more about what we mean by fooling functions, let's introduce some terminology. So y here will be y1 through yn. This is our collection of fully independent random variables. And then we'll let x be an arbitrary k-independent family of random variables such that each of the xi's are distributed in the same way as the corresponding yi. And there's some function f that we want to fool, which is a function from Rn to R. And we'd like to be able to show that the expectation of f of x is roughly the expectation of f of y. So we've got all the yi have been fixed, but we want to know that for any x that's k-independent with the correct distributions on each variable, the expectation is close to what it should be. And one thing to note here is that if f is a polynomial of total degree at most k, then these expectations in fact are going to be exactly the same, because your polynomial of degree at most k is a sum of monomials of degree at most k, and each of those have their expectations determined by k-independence. And in fact, as we'll see a little bit later, the problems of showing that something's fooled by k-independence and approximating by degree k polynomials are very closely related problems. Moving on to a little bit of notation, we say that k-independence epsilon fools f if, for all such k-independent x, the absolute value of the difference between the expectation of x and the expectation of y, or f of x and f of y, is at most epsilon.
Do you assume some normalization of f x?
Yeah, this is assuming that the x is, yeah, so, I mean, really I should add to this terminology like with respect to y, and then also assume that the xi's are distributed in the same way as the y's. And we'll use the notation that a is approximately equal to sub epsilon b, just to say that the absolute value of the difference is O of epsilon. And really, when we're talking about epsilon fooling something, we'll really generally replace it with O of epsilon fooling, because if you're only off by a constant, you can just make epsilon smaller. Okay, so one thing that you can look at is, let's look at this from a very theoretical level. Let's suppose that the yi are Bernoulli random variables. They're plus or minus 1 with equal probability. Suppose that we've got some fixed arbitrary function f. For the moment, we don't even care what it is. And we just like to see how far off can k-independence give you. So, for example, what is the biggest possible expectation that we could have for f of x, where x is k-independent, and again, the individual variables are the same as for the y's? Well, it's not that hard. Let's, for every string a sub I of possible values, we'll let p a sub I be the probability that we get that particular string, which is always positive. K-independent says that if we fix any k of the entries and sum these probabilities over all strings with those fixed k entries, we get 2 to the minus k. And with respect to these conditions, we want to maximize the expectation. So we want to maximize the sum of p of a times f of a. And this is just a linear program, which, I mean, as a linear program, it's somewhat complicated and perhaps not particularly insightful, but we can look at the dual program to this, which actually is a lot easier. And if you work out all the details, the dual program is the following. What we want to do is we want to find g, which is a polynomial of degree at most k. Or in general, if your variables take more than 2 values, so if each of your coordinates has more than 2 values, we want it to be a sum of functions that each depend on at most k coordinates. And we furthermore want g of a to be bigger than or equal to f of a for all a. And we want to minimize the expectation of g of y. And it's easy to see that this gives us an upper bound, because the expectation of g of y is equal to the expectation of g of x, because it's a sum of these, I mean, it's a degree k polynomial. And because g is bigger than f pointwise, this is bigger than the expectation of f of x. And so again, fooling f with k independence is very similar to saying that f can be well approximated by a degree k polynomial. Okay, so from here on, we're going to let y be a standard Gaussian. A lot of the papers where we've worked with this, we've actually wanted it to work for Bernoulli random variables. And in fact, almost everything I'll say here will generalize to Bernoulli random variables for a few reasons. One, we have the same sort of moment bounds for polynomials of Bernoulli random variables as the ones I'm using for Gaussian random variables. For Gaussian random variables, I also use a number of anti-concentration results that, you know, the probability that your Gaussian is in some small range is small. But as it turns out, if you have a polynomial with low influence, meaning no one coordinate has a major impact on the final value, the invariance principle says it behaves more or less like a Gaussian, like the same polynomial of Gaussians, and hence you will still have anti-concentration. And if you have high influence random variables, there are a number of regularity lemmas that say basically after fixing some of the high influence random variables, you can reduce to the low influence case. So you use some of your extra independence to fix a bunch of the high influence variables, and then for the rest of your independence, you're just dealing with a low influence polynomial. Okay, so let's stick with, a lot of these techniques are a lot easier if you can sort of reduce the dimensionality of your problem. As I've said, a lot of the idea involves approximating some function by a degree k polynomial, but approximating functions in many, many, many dimensions by high degree polynomials can become very, very complicated. So it's a lot easier if you can write your function as some function in just a few polynomials in your original variables. So for simplicity, let's assume that, you know, so now I'm calling my variable z, which could be either x or y. So that f of z is some function little f applied to w dot z. So it depends on some linear function in z. And now the idea is, instead of approximating big F by a polynomial, let's just approximate little f by a polynomial and apply this approximation to w dot z. Now, if little f is smooth, there's a very convenient way to do this, because if you have a smooth function, it has a Taylor series, and not all the fonts are showing up the way they should. I forgot this. I really should have remembered to bring my laptop. Anyway, yeah, this is the Taylor series, and there's a Taylor error term. Sorry, throughout this talk there are going to be a number of poorly fonted things. Anyway, but you've got an error that looks like absolute value of z to the k over k factorial times the size of the kth derivative. And so if k is even, that error is in fact a polynomial, so your k independence is going to determine its size. And if we want to look at the moments of w dot z, which is our variable little z here, well, we've got the expectation of w dot x to the k times the size of the kth derivative over k factorial. That's our Taylor error. And from the hypercontractive inequality, which gives you bounds for moments of a polynomial, or in general, just knowing that your linear polynomial in Gaussians is just a Gaussian, this turns out to be, the size of this is roughly the size of w to the k times k to the minus k over 2 times the size of the kth derivative of f. So if f has nice bounds on its higher order derivatives, you can approximate by your Taylor series and get nice bounds on the expectation of the Taylor error. So unfortunately, most of the functions that we're going to care about are not smooth. In particular, I mentioned this polynomial threshold functions. Well, the simplest one is a linear threshold function. So here we just want to know whether we take an indicator function of w dot z. We get 1 if w dot z is bigger than some constant a and 0 otherwise. So the problem here is that little f is not a smooth function. It's got this discontinuity at a. It doesn't have it. Well, we could make a Taylor series somewhere, but it's not going to converge very well. So what do we do? Well, the idea is we're going to replace f by a smooth approximation f tilde. And since we're trying to prove our approximation for f and not f tilde, we've got to do a number of steps to actually show that it works. But basically what we're going to do is we're going to try and prove the following chain of approximations. We start with f of y and then approximate by f tilde of y and approximate that by f tilde of x and finally by f of x. And so for each of these steps we use slightly different methods. For the first step, f of y and f tilde of y, since f and f tilde approximate each other, that's basically where it comes from. But unfortunately, since we're approximating a discontinuous function by a continuous function, it has to have an error somewhere near the discontinuity. So what we need to know that the probability that w dot y is near that discontinuity needs to be small. So we need some sort of anti-concentration result for w dot y. For the second thing, we've got f tilde of y and f tilde of x, but f tilde was smooth. We do what I said before. We approximate by a Taylor series and just show that the expectation of the Taylor error in either case is small. And note that k independence determines the expectation of the actual Taylor polynomial. So we use polynomial approximation, we use moment bounds. And for the last step, it's very similar to the first step, but now we need anti-concentration of w dot x instead of w dot y, which is harder because y is fully independent. In fact, in this case, w dot y, we know it's a Gaussian. We've got very good anti-concentration results for that. W dot x, we really don't know what it looks like, but we'll use some of these techniques to be able to derive this anti-concentration from our anti-concentration results for w dot y. And I'll get into that a little bit more later. Okay, so on the other hand, so this is a great plan. The problem is, how do we do our smoothing? How do we replace f by f tilde? Well, one of the oldest techniques for smoothing functions, for approximating by smooth functions, is this idea of mollification. What we'll do is we'll let f tilde be f convolved with some smooth function rho. And, well, the idea is to show that this thing is smooth. We know that if we want to take the derivative of a convolution, we can take the derivative of either side. So the kth derivative of f tilde is just f convolved with the kth derivative of rho. So if rho is smooth, this thing is smooth. If rho has good bounds on its higher order derivatives, this thing has good bounds on its higher order derivatives. Great. So what we need is bounds on the derivative of rho, so we can get bounds on the derivatives of f tilde. And we'd like these bounds to be strong, because remember, our Taylor error depends on the size of the kth derivative of f, and as we'll see slightly later, if our bounds aren't strong enough in some cases, it really makes this method not work at all. Also, though, we want f tilde to approximate f, and so in the mollification context, the way you do this is you want rho to be sort of what people call a smooth approximation to the delta function. You want its integral over all space to be 1, so you're sort of, so convolving with rho is sort of averaging it with nearby stuff. And furthermore, we want it to decay rapidly. We want the size of rho to be very small when x is large. So convolving with rho is sort of averaging your value with a bunch of nearby values. So unless f is discontinuous at that point, you're averaging with nearby values which are all close to your original value, and you're in good shape. Okay, so in the way we're going to construct rho for this application, so I mean, we wanted to have those results for approximation, in particular decaying near infinity, and we also wanted it to have very tight bounds in its higher order derivatives. So to construct this function, we're going to use the Fourier Transform, which is where the name of this method comes from. But before we do this, let's briefly review some basic properties of the Fourier Transform. Importantly, the Fourier Transform interchanges differentiation with multiplication by x. The Fourier Transform of the derivative is x times the Fourier Transform, and vice versa. And what this means is that it interchanges smoothness with decay at infinity. Because we say a function is very smooth if you can differentiate it a lot of times and it remains small. And on the other hand, we say a function decays rapidly at infinity if you can multiply it by x a lot and it stays small. So since the Fourier Transform interchanges differentiation and multiplication by x, it interchanges smoothness and decay at infinity. So what we want rho to be is we want it to be very smooth. We want to have sharp bounds in its higher order derivatives, and we also want it to decay at infinity. So if we want to think of rho as the Fourier Transform of something, we want it to be the Fourier Transform of something that's very decayed at infinity and also smooth. So for very decayed at infinity, we're going to use going to be the Fourier Transform of a compactly supported function, because really you can't decay at infinity faster than that. So rho is the Fourier Transform of a compactly supported function. So for example, rho could be the Fourier Transform of the following smooth compactly supported function on -1, 1. So what do we know? We know that the size of rho to the k in this case is O of 1, because if you want to compute the kth derivative, what you do is you take the Fourier Transform and multiply by x to the k. X to the k is bounded by 1 on -1, 1. Then you take your inverse Fourier Transform, so you're bounded. And remember, this O of 1 doesn't depend on either k or x. Next, we want decay at infinity, and to be really weak about this, for every n, we know that it decays faster than x to the minus n. Because we know that when we multiply by x to the n, that's the same as taking an nth derivative of the Fourier Transform. The Fourier Transform is still bounded after taking an nth derivative, so taking an inverse Fourier Transform back, there's some absolute bound that is bigger than rho of x times x to the n. Furthermore, because I made the inverse Fourier Transform of rho to be 1 at the origin, this means that the integral of rho over the entire line is 1, which is something we wanted. Furthermore, so we can't quite just use this rho, because this rho, it does have decay at infinity, but it's still got some finite width. And if we always convolved with this rho, then we'd always have errors within some finite region of our discontinuity, and since there's some finite probability that we'll land in that region, this technique will never show that we can get errors smaller than some constant. So we need to be able to scale it to make it very, very concentrated. So we let rho sub c be c times rho of cx. So this scrunches it by a factor of c and blows it up by a factor of c. Now, the size of the kth derivative is O of c to the k, and we have that its decay is now correspondingly more rapid, and its integral over the entire line is still 1. Okay, so now we can write f tilde. So let's write f tilde sub c is our indicator function from a to infinity convolved with rho sub c. So what are the properties of this? Well, its kth derivative is O of c to the k, and this holds everywhere. That's good. We want bounds on the error between f and f tilde. On the one hand, this should be at most 1 because f is bounded by 1, and we're convolving with something. And furthermore, this is at most c times the distance to the discontinuity to the minus n. And this is basically because of the rate at which rho decays. Yeah, so polynomial approximation, my fonts are doing wonky things. Great. Anyway, so what this should say is, okay, we want to show here that the absolute value of the expectation of f of y minus the expectation of f of x is small. So our bounds, we get the size of the kth derivative, which is c to the k, and then we get the size of the kth moment, which is size of w to the k times k to the k over 2, and we're dividing that by a k factorial, so it's k to the minus k over 2. Putting this all together, we've got something that's O of c times the size of w over square root of k all to the k. So we've got something to the k. The something has a root k in the denominator. So as long as the something is small and the k is at least log 1 over epsilon, we're in good shape. So we need k to be at least something like 2c size of w squared, and we also need it to be at least log 1 over epsilon. Next step, we want the anti-concentration. We need that the expectation of f of y minus the expectation of f tilde of y is small. So we're going to use the obvious approximation. It's bounded by the expectation of the absolute value of the difference. And we note that f minus of f tilde is small except when we're near a. And furthermore, w dot y is anti-concentrated. So let's remember f minus f tilde is big O. Now I'll just do it, it's either O of 1 or O of c times x minus a to the minus 2. And ick. So sure. So the idea here is we're going to write out a geometric series. We're going to say that if our error is at most, let's see, if it's at most 2 c inverse, then our error is at most 1. So we've got at most the probability that w dot y minus a is less than 2c inverse. So we've got at most 1 if it's in that range. Now if it's within 4c inverse, between 2c inverse and 4c inverse, I should say, our error is at most a quarter. So this should be plus a quarter times the probability that our absolute value minus a is less than 4c inverse, and then plus 1/16 of the same thing with 8c inverse, and so on, because remember we go down like the square of our distance. And now, remembering our anti-concentration results, this probability is going to be something like 2c inverse over size of w, I think. And this is going to be like 4c inverse over size of w, and this is going to be 8c inverse over size of w. But remember, this is being multiplied by 1 and a quarter and a 16th. So these things are going down by powers of 4. These things are going up by powers of 2. This geometric series converges. And in the end, we get O of 1 over c times the size of w. So, okay, so the thing to get out of this is that we need that 1 over c times the size of w needs to be much, much less than epsilon, basically, in order for this term to be reasonable. Okay, so that's that. So next we need to show an anti-concentration bound for w dot x. And again, like this is basically the same argument, but now we need anti-concentration for w dot x. So again, we have an error that is the same gibberish in this font, but should be exactly this summation, only now all the y's are replaced with x's. So what we have these bounds for y, we know that these probabilities that were within those ranges are good for y, but we need them for x. So really what we want to do is we want to show that k independence forces this function g of z, which is the indicator function that we're between a minus b and a plus b of w dot z, to not have too large an expectation. Now, you might think that we haven't gotten anywhere from this, because we started by saying let's try and fool this function, and we've reduced it to the problem of let's try to fool this other function. But the point is, their original problem, we had some function, we want to show that we're within epsilon. Here we don't necessarily want to show that we're within epsilon, we just want to show that we're not too much bigger. We want to show that this probability isn't more than, say, 8 times what it's supposed to be. And for that, what we can do is we're going to go through the same mess as we just did, but we're going to make sure that g is strictly less than g tilde everywhere. So this means that sort of when we're running our first steps, yeah, sure, the expectation of g of y is near the expectation of g tilde of y, and that's near the expectation of g tilde of x, but hey, that's strictly bigger than the expectation of g of x. So we'll be good when we do it this way. So what we're going to do is we're going to obtain g tilde. Instead of mollifying g, we're going to mollify something like twice an indicator function of twice the interval. So that, you know, since we're much bigger and go much further out, it's not hard to cook this up in such a way that our g tilde strictly upper bounds g. But, I mean, the actual expectation of twice this doubly large indicator function should only be about 4 times as big as the thing we're trying to bound in the first place. So we'll be in good shape. Okay, so for fooling linear threshold functions, we have the error from approximating f by f tilde. That's roughly 1 over c times the size of w. So we need c to be at least 1 over epsilon size of w. And to have a small error from our Taylor error, we need k to be at least 2cw squared or so. So k we can get away with being O of epsilon to the minus 2. So what you need to fool epsilon and to epsilon fool your linear threshold function is O of epsilon to the minus 2 independence. Okay, so that's sort of the first application. Now I'm going to talk about a few tricks that we can use to make this work out more conveniently, and I'll get back to another problem we can solve with this a little later. But one of these things is, so in sort of that last step of the inequality, we wanted a convolution so that g tilde was strictly bigger than g. And to make that work, it's actually convenient to have our rho be a strictly positive function. Because this means when we do our convolution, our f tilde is always between the inf of f and the sup of f. A lot of the analysis is made easier by doing this, and in particular, it guarantees that our g tilde is strictly bigger than 0 and doesn't accidentally dip below 0 near the boundaries. Okay, so I mean, how do we do this? Well, we can let rho be the square of the Fourier transform of, again, a compactly supported function. We can normalize by letting the integral be, well, the integral of rho is just the L2 norm of b, and we're going to set that equal to 1. Note that that's all, so the problem now is, for a compactly supported function, we knew how to bound its higher derivatives. How do we bound the higher derivatives here? Well, again, this is a mess, so let's use the board. But the point is that our kth derivative of rho, well, we could write it as, we want to take the kth derivative of b hat times b hat bar, and, well, you can take kth, you differentiate both of these, so you end up with a sum of k choose j. And now, I mean, for one thing, in this case, I'm actually going to bound the L1 norm of rho here, which is actually, if you think about it, what you want to do. Because you're going to be convolving rho with something that's, say, has a bounded L infinity norm, and you want to sort of bound the size of the error. So you really often want to get the L1 norm of this. And so now we've got a bunch of products of b hat, the jth derivative, and b hat.
You mean of the kth derivative?
Yes, of the kth derivative, sorry. So the point is we've got sort of an inner product of these, and really, I mean, these should be like, we should be taking the L2 norm of this times the L2 norm of this and using Cauchy-Schwarz. And so now instead of taking derivatives of the Fourier transform, for one thing, the L2 norm is preserved by Fourier transform, so instead of taking derivatives of this guy, we're going to be taking the Fourier transform and multiplying by x. So what we've got is sum of k choose j, and now we have x to the j b L2 times x to the k minus j b L2. And the point is that if b is compactly supported, multiplying by x doesn't multiply it by more than however big your support is. And so we get this sum of k choose j, and this thing looks like the L2 norm of b squared times the size of the support of b to the k. And well, this sum of binomial coefficients is 2 to the k, and we get a sum of, and the size of b squared is 1 by our initial normalization. So we get is at most 2 times the size of the support of b all to the k. Where by the size of the support here, I mean sort of the biggest absolute value of any point in the support. So we get a nice bound here, and based on the size of the support. Okay, and so another thing that we're going to want to do is we're going to want to do multidimensional mollification. So if you'll notice with our linear threshold functions, we got kind of lucky. We could write the function that we cared about as a function of a single polynomial in our actual coordinates. And so we only needed to work with sort of a one-dimensional function that we needed to smooth out. But in general, we're not always going to be so lucky. So we're going to want to have a row that's a certain function of several variables. So one thing that we found out that works very well for a lot of purposes is we're going to use the same strategy as before that I just described for a positive convolving function. We're going to let b of r be an appropriate normalizing constant times 1 minus the L2 norm of r squared for r less than 1 and 0 outside that. Note that this is no longer actually a smooth function, but its decay at infinity will be good enough, as we'll get to shortly. And this is a mess, but basically what we're going to do is we're going to bound the integral of x squared times rho of x dx. And I'll guess I'll not get into, fine, I'll do this very briefly. This is a sum of xi squared times the Fourier transform of b squared. Note that this is something squared that we're integrating. It's an L2 norm. We can interchange this xi with taking the derivative. We do some computations, ... This is equal to O of m squared, where m is the dimension. And what this means is, for one thing, since rho is positive and has integral 1, you can think of it sort of as a probability distribution. And this is the expectation of x squared. And since that's finite, it means that we're somewhat concentrated. And in particular, this isn't showing up, but what it means is that our integral over all of space, where the absolute value of x is bigger than r of rho of x dx, is going to be at most m squared over r squared. And that bound will turn out to be basically good enough for everything that we want to do. If you needed tighter bounds, you could of course make b more smooth. It would require being a little bit more clever, perhaps. Also from the bounds that we had before, the kth derivative, and in fact, the kth directional derivative in any particular direction, or at least a unit vector direction, is at most 2 to the k. And we'll use that later. Okay, so fooling intersections of half spaces. We now have enough to deal with this. So now instead of f being a single linear threshold function, it's going to be a product of m different linear threshold functions. So we want to control which side of several different half spaces we are in at the same time. So now instead of depending on just one w dot x, it depends on a bunch of wi dot x's. Let's, for convenience, let b sub I be an orthonormal basis of the wi's. And now we have some function L of x, whose coordinates are just bi dot x. And our capital F is just some function little f of L of x. So again, this is sort of the same idea, but now instead of f being just big F being just some function of w dot x, it's now some function of this m-dimensional function of x. So now we're going to use multivariate FT-Mollification. The basic plan is the same. We convolve little f with this row, or a scaled version of this row, to get f tilde, and we prove this chain of approximations. Yeah, we get f tilde by now convolving with c to the m times rho of c times x. Okay, so anti-concentration, again, the math is being wonky. So, okay, so we need a bound on how far apart f is from f tilde. So let's suppose that x is a distance of at least d from any of the hyperplanes. So this is after you take L of x, the point that you end up with is a distance d from any of the hyperplanes at which we have these discontinuities. Then the claim is that f of x minus f tilde of x is at most O of m over cd squared. And the reason for this is that, well, since within a distance d we're on sort of the same half of all of the hyperplanes, if we integrate if we're integrating against rho on that sphere of distance d, we're just integrating against exactly the value that we want. And all of the error comes from integrating against stuff outside that range. But we already had a bound for what we got with integrating stuff outside a range. And the c comes, of course, from the fact that we rescaled rho by a factor of c. So it would have been just m squared over d, but we rescaled rho, so it's m squared over cd. And so what this means is that basically our error is roughly the probability that x is within m over c of some hyperplane. Because, I mean, if d is roughly m over c, then this is order of 1, but it falls off quadratically as d becomes multiples of that, and as we sort of saw before, this falling off quadratically means that we get this geometric series of terms that we don't care about. So
subspaces determine a function? Is it the supremum of the characteristic function of the half?
It's something like the product of the characteristic functions.
Okay. Intersection.
Yeah. Okay, so our error is roughly the probability that with an m over c of some hyperplane, there are m hyperplanes. And remember, we actually dotted with the bi's, which were unit normal vectors. So this error probability is going to be O of m squared over c. So that's what the error we get is from our anti-concentration problems. I won't do the same thing for x because the trick is the same. Fine, we need c to be whatever it needs to be. So the next step is polynomial approximation. Now, for this step again, we take f tilde, we approximate by its degree k minus 1 Taylor polynomial at 0. Now, since we're in several dimensions, we need to know what we mean by this. And in this case, I just mean we take everything up to degree k minus 1 in all combinations of directions. Again, we've got this problem of what's our Taylor error here. And one trick for doing this, we can look at the Taylor error along the line from 0 to wherever we happen to land. So, I mean, in particular, we restrict our function to that line, and it turns out that this Taylor series approximated to that line is the Taylor series of the function approximated to that line. So we just look at the Taylor error along this line, we get it's the size of the kth derivative along that line times the times the size of L of x to the k over k factorial. The size of the kth derivative was at most 2c to the k. The expectation of the kth derivative, well, in each coordinate it's just a Gaussian. So in each coordinate it would be like k to the k over 2. There are m coordinates, so that's like m over k to the 2 times k to the k over 2. And So putting this all together, the error is like 4mc squared over k to the k over 2. So as long as m is bigger than, mc squared, or to make c as big as it needs to be, m to the 5th epsilon to the minus 2, we'll be in good shape. Because then we'll be taking this small thing to the k, and k is pretty big. On the other hand, we did a kind of lousy approximation here. We approximated the size of L to the k as just m to the k over 2 times the bound on each of the coordinates. And if the coordinates were somehow highly correlated, this would be an okay bound. For example, if they were all the same. But they're not. In fact, since we picked an orthonormal basis to define L, if x were actually a random Gaussian, these coordinates would be completely independent of each other. So we should expect the bound to be much smaller. And in fact, there's this bound on moments of a quadratic form of a Gaussian. And again, I'll have to write this down to make it convenient. So what you have is you've got Q a quadratic form. And we're looking at the expectation of the absolute value of Q of x to the k. And there's so the theorem is that this bound is O of the expectation of Q of x. So there's sort of a bunch of terms here, and plus the Frobenius norm of Q. This is the sum of the squares of the eigenvalues times root k, plus the infinity norm of Q. This is the operator norm. This is the size of the biggest eigenvalue times k, all to the k. So the way I like to think about this, there's sort of three different ways that Q could behave. One, you could take Q of x to be like the sum of the square. Firstly, you've got a quadratic form. You can always diagonalize it. When you diagonalize, basically, your quadratic form is just a sum of chi-squared random variables that are independent of each other times certain weights. So on the one hand, you have the expectation of Q. I mean, if you've got like a bunch of chi-squared random variables with really small weights that you're adding together, it basically looks like a constant. So your kth moment is going to look like that constant to the k. The second term, well, Q2, the Frobenius norm, this is, on the other hand, if you've got no constant term, if, say, your weights all add up to 0, then you've got a sum of independent chi-squared random variables. They've got no expectation. But since you've got a sum of a bunch of different things, they're all independent of each other, you expect it to be a Gaussian. And Q2 turns out to be what you expect the variance of this Gaussian to be. And so if you're approximating this giant sum of independent things as a Gaussian, that's what the kth moment should be. But clearly that's not always accurate. Suppose that you just had one chi-squared random variable. Clearly its kth moment is not going to look like the kth moment of a Gaussian. It's going to look like the 2 kth moment of a Gaussian. So this last term is you just take the biggest eigenvalue, the biggest chi-squared that fits inside of that, and take the kth moment of that. So that's where this comes from. But it can give us a better bound on the expectation of L of x to the k, since L of x squared is a quadratic form. Its expectation is m, its Frobenius norm is m, and its L infinity norm is 1, so we get the following for our bound. And plugging this in, we can actually get away with k being O of m to the 4th times epsilon to the minus 2. So this quadratic form moment bound saves a factor of n. Okay, so again, here's one more technique, and then I'll get into degree 2 polynomial threshold functions. So one thing that we want to do is we want to build an f tilde that A approximates f and has B very sharp bounds on its derivatives. Now, there's a problem here, though. There's sort of a fundamental limitation that f is typically going to be bounded. So let's say we want f tilde bounded and have very fast bounds on its higher order derivatives. The problem is the derivatives are never going to decay faster than exponentially, unless it's like a constant or something. And one way to see this is just look at the Fourier transform of f, which it should have because it's bounded. And if you look at the Fourier transform, then it's going to have some amount of width. Then you take derivatives of f, you're going to be multiplying the Fourier transform by x to the k. But since the Fourier transform has some support outside of 0, unless it's a polynomial, This means that multiplying it by x to the k will at least multiply that part of it by however far you are from 0 to the k. You're not going to be able to decay faster than exponentially. And this is a problem. On the other hand, you can actually, if you only care about the value of f on positive numbers, you can do a little bit better. So for example, if f tilde only needs to be bounded on positive numbers, you've got things like cosine of square root of x. Now, since cosine of x has terms, x to the n, 2n over 2n factorial, this thing has coefficients x to the n over 2n factorial. So it's got much better higher order derivatives than you'd expect. On the other hand, it's only bounded on positive numbers. On negative numbers, it looks like cosh of root x and blows up exponentially. But if somehow we were taking f and it only ever needed to be evaluated on positive numbers, the fact that it's a really terrible approximation on negative numbers doesn't matter to us. So in general, if we have an x that we want to approximate by f tilde, but only care about f tilde on the positive numbers, well, we can write g of x as f of x squared. So this is sort of a function that is symmetric and only sees the positive values of x. Now we get f tilde by taking g, convolving it with our row, and then evaluating it back at square root of x. And it turns out that this thing will have derivatives that decay like, instead of c to the k, they'll decay like c over k to the k, which is a lot better. And furthermore, this f tilde approximates f now on the positive reals, though again, you can't evaluate these things on negative reals because you'll get big exponentials and it will be horrible. Okay, so using this we can fool degree 2 polynomial threshold functions. So what we want to do is we let f of x be this indicator function from 0 to infinity of p of x, where now p is a degree 2 polynomial. Note that we cannot now naively use the FT-Mollification method. So again, we've got a mess, but if we're trying to approximate f by a smooth thing, suppose even f were smooth, and now we're going to use our Taylor error. Well, our Taylor error looks like the size of f to the k times the kth moment of p over k factorial. Now the size of f to the k is, in the case we're looking at, looks like c to the k. But now the kth moment is the kth moment of a degree 2 polynomial. So that instead of looking like k to the k over 2, looks like, whatever our size of p is times k to the k. Again, over k factorial. The k to the k cancels the k factorial, and now we get something that looks like c times the size of p to the k. But this means that if c is big relative to the size of p, this actually won't get any better as we increase k. In fact, the errors will get worse as we increase k. And since we can't do that, we'll never be able to make c big enough, so we'll never be able to convolve with something that's concentrated enough, and it just won't work. On the other hand, there's a way to get around this. This thing says that we're going to, run into problems with, threshold functions of, say, a Gaussian squared. But clearly a Gaussian squared, we could just get threshold functions of the Gaussian, and we'd be okay. So we want some sort of decomposition. So if it's got sort of a few big terms that look like the square of a Gaussian, we want them to just see where those Gaussians lie. So we're going to decompose p into a couple of functions. So first off, we're going to pick a normalization. Let's assume that the L2 norm of p is 1. This is just the expectation of p squared should be 1. What we're going to do first, we're going to write p of x as a quadratic form plus a linear form plus a constant. And furthermore, we're going to decompose the quadratic form. We're going to decompose it so we can always diagonalize our quadratic form, and we're going to split sort of the eigenvalues into 3 classes. Q plus takes all the eigenvalues that are bigger than some delta. Q minus takes all the eigenvalues that are less than minus delta. And Q0 takes all the eigenvalues that are in between. And the idea of this decomposition is that both Q plus and Q minus are positive definite. So since we only ever need to evaluate them on positive numbers, this trick about functions that we only never need to evaluate on positive numbers is usable. Q0, on the other hand, has a small L infinity norm. And so if you remember the quadratic form moment bound, it's got things that look fine, that look like a Gaussian, unless your L infinity norm is big. But since the L infinity norm is small, we should be okay. So formally, what do? We define m of x to be, we've got 4 coordinates. We've got square root of q plus, square root of q minus, q naught minus the trace of q naught, just so that this term doesn't get in our way. And then we've got the linear term. And we let little f is in fact equal to this indicator function applied to, w squared minus x squared plus y plus z plus the trace of q naught plus c. And big F is just little f of m of x. So now what we do is we take little f and we mollify it, and let's see what we get. So the first thing is we've got anti-concentration to deal with. F minus f tilde is small unless m of x is within about c inverse of the boundary between its 0 and its 1 regions. And things are a little bit difficult here, because beforehand we just knew that we were okay unless the value of a polynomial were close to the boundary. On the other hand, we can move m of x a little bit. We can move it c inverse. How much can we change the effective value of the thing we're taking an indicator function of? Because remember, we were taking an indicator function of a w squared minus x squared plus some linear stuff. And this means that if we move by c inverse, we can move the value of this thing that we're taking our indicator of by something like, w times c inverse plus x times c inverse plus c inverse plus some stuff. So in order for us to not sort of automatically be very close to the boundary, we need that the first 2 coordinates are small. Fortunately, as it turns out, size of m1 and size of m2, it's not hard to show, are about delta to the minus a half, O of delta to the minus a half, with high probability. And this is just because, since they only take large eigenvalues, there can't be too many of those eigenvalues, and so the total expectation can't be too big. And from that, we have that f minus f tilde is going to be small unless p of x is within about delta to the minus a half times c inverse of 0. And, well, we've got Gaussian anti-concentration. In fact, there's an anti-concentration result for polynomials of Gaussians. And given the normalization of p, our error is going to be about O of delta to the minus a quarter times c to the minus a half. Next, polynomial approximation. So our error is, again, the size of the kth derivative times the size of m to the k, the expectation of that, over k factorial. Kth derivatives like O of c to the k. For size of m, we've only got 4 coordinates. Let's bound them each separately. So the moments of m1 and m2 are like the k over second moment of a quadratic. And it's not hard to see that that's, so k to the 1/2 to the k plus delta to the minus a half to the k. These are just coming from, the delta to the minus a half is coming from the fact that it's got a big expectation, perhaps. And the k to the minus a half is just from bounds for quadratics from the hypercontractive inequality. So for m3, this is the expectation of q naught minus its trace to the k. Here we use this thing. So that's either L2 norm, which is at the Frobenius norm, which is at most 1, times k to the 1/2 to the k, or the other term, which comes from the operator norm, which is at most delta, times k to the k. The last one we have is for m to the 4th, which is the linear term, so that's like O of root k to the k. So we get a total error. We've got those 4 terms, all to the k. So putting it all together, what do we need to be true for our total error to be at most epsilon? Well, we need each of those terms that we saw in the last thing to all be smaller than 1. So we've got something much smaller than 1 to the k. We want k to be at least log 1 over epsilon, so when we've got 1/2 to the k, it's actually small. And then we need that delta to the minus a half times c to the minus a half that we got from our anti-concentration bounds. That should also be much smaller than epsilon. But we can get away with c being roughly epsilon to the minus 4, and delta being epsilon to the 4, and k being epsilon to the minus 8. And if you twiddle with the exact parameters, you can make all the things that are supposed to be less than 1 actually less than 1. And so you can show here that epsilon to the minus 8 or so independence epsilon fools degree 2 polynomial threshold functions. So there's actually a new result that was more new when I originally gave this talk. that you can actually fool degree D polynomial threshold functions. Unfortunately, you need k to be something like epsilon to the minus 2 to the O of D independence. But what's the basic idea here? Now instead of moment bounds for degree 2 polynomials like this, you need moment bounds for arbitrary degree polynomials. And basically there's a result that says that for an arbitrary degree polynomial, it's got the moment bounds you'd expect from sort of a Gaussian with its variance, unless it's got some big component that looks like a product of two other functions. So what type of things have high moment bounds? You've got high moments if you've got like a single Gaussian to a large power, then that has very large moments. Or one Gaussian times another Gaussian, or something of this form. But this gives us a natural decomposition. So we have a structure theorem. Basically, you've got your polynomial, it's got small moments, unless it's got the component that looks like a product of two other things. And in that case, you just make those two other things sort of new variables. You write it in terms of your old thing minus those and these new things. And you sort of then decompose these recursively. You get some big number of things that you're writing your original polynomial in terms of. But fortunately, all of these things actually have small moments. Then you use FT-Mollification in some gigantic number of variables. And have to be a little bit clever about, in some directions you need it to be more concentrated than in others. But those are details, and it works. So further work for this technique. We could probably use a better multidimensional version for the function that we use to mollify with. The one that we use seems to work, but it's not clear in any sense whether or not it's optimal. Also, we're always looking for new applications of this technique. We have a few. It'd be nice to have more. Here are some references to papers that were used in the development of this technique. That's all I had to say. Are there any questions?
Epsilon to the minus 2 to the d, do you suspect that can be improved?
I suspect it can be improved. In fact, I think that the actual answer is it should be like d squared times epsilon to the minus 2. But I have no idea how to prove anything approximating that.
Was that earlier work on the same topic? And I'm totally ignorant. So who worked on it and what
let's see. I don't know. I don't think there was anyone who had fooled degree 2 polynomial threshold functions before we came along. I think there were several people who had sort of other technique. So there had been lots of people who had written papers that show you could fool linear threshold functions, and sort of a lot of them, instead of using this framework, they just went and used sort of standard results from approximation theory. And I think that sort of in doing this, we've discovered that some of this, a lot of this technique is sort of rediscovered from what people did back in the day for approximating by polynomials. But for a lot of this stuff, it really helps to know the inside of your machine and be able to actually use it so that you can get this thing done in multiple dimensions and figure out exactly where your errors are and exactly what your bounds and your derivatives look like.
I actually have a few other potential applications, but I'll discuss them with you later. So let's thank Daniel again.